Sometimes we have this kind of problem. Sketch the region of integration for this double integral here, iterated integral, and write an equivalent integral with the order integration reversed. So what's going on here? What are the bounds on this original integral? So x is running from 0 to 2. Y is running from x squared to 2x. So we need to, in order to best do this, let's graph what's going on here. Okay, x is running from 0 to 2. That's that there. Y, we have y is equal to x squared is one bound. And y is equal to 2x is a second bound here. So y is equal to 2x, and then y is equal to x squared. Right, an equivalent integral with order integration reversed. So before we were slicing this vertically, now we slice this horizontally, and this ends up feeling a lot like the problem that we did a couple of videos ago here. What's our y bounds? Y runs from 0 to 4. X runs. We need to write our y in terms of x equations as x in terms of y. How do we do that? This one is x is equal to y over 2. And this one is x is equal to square root y. And the lower bound here, the left bound, is y over 2 square root y. So what is our iterated integral now integrating in the opposite order? Y runs from 0 to 4. X runs from y over 2 to square root y. The inside function, the integrand, does not change. And that's what we have. Note one thing that I haven't really made a big point about, but maybe here's a good time to make a little bit of fuss, is that the outside bounds on your integral always need to be constants. The inside bounds are allowed to be functions of some other variable. So like here we write x as a function of y, but the outside bounds always have to be constant. Y is 0 to 4, those are constants. X runs from 0 to 2, those are constants. If you ever give me an answer in which there's, y is equal to x squared or x or 2x, some expression involving x on the outside integration, I automatically know that's incorrect. So make sure your outside bounds are always constant in the order, when you're thinking about switching the order integration. Okay, maybe again in a similar spirit here, evaluate this integral. The integral where y runs from 0 to 4, x runs from square root y to 2 of square root of 4x squared plus 5y, all of that dx dy. So this first part would be asking us to find an antiderivative of square root of 4x squared plus 5y with respect to x. And let's just say here, if you're being asked for square root of 4x squared plus 5 times let me just put some constant here, constant c here. We're going to think of y as a constant. This would require trigonometric substitution. And that's going to be a lot of work. It would be possible. Let's try to take the easy way out. Let's try to do this more simply. let's think about swapping the order. So I didn't tell you sketch the region integration and write an equivalent integral with the order integration reverse, but that's how we're going to tackle this. So what are our bounds here? Y runs from 0 to 4. X runs from square root y to 2. Okay, y runs from 0 to 4. X runs from, we're going to have x go all the way out to 2. So let's see here. We are going to deal with the curve square root y is equal to x. Squaring both sides gives us y is equal to x squared. So we need to plot y is 0, y is 4, y is x squared, x is 2. We need to plot all four of those things. So here is y is equal to 4. Here is y is equal to 0. We need y is equal to x squared. And x is equal to 2. So which region here corresponds to these inequalities? It's this lower right region down here. So common mistake would be to come up with the wrong region. Common mistake would be to fill in this region, but this doesn't correspond to this region here. Would be y is from 0 to 4, but this would be x is running from 0 to square root y. We want x to run from square root y to 2. So the way that this is set up is horizontal slices, but instead we want to slice this vertically. And so what are going to be our bounds here? X runs from 0 to 2. Y runs from 0 to x squared. And so what we do, okay, this is equal to the integral from x runs from 0 to 2. Constants on the outside, then y runs from 0 to x squared, square root of 4x squared plus 5y dy dx. And now our life is a lot easier. Why is our life a lot easier? Because integrating this with respect to y, find antiderivative of this with respect to y, is a lot easier because we just have this is linear in y under the square root. There's no y squared here. So maybe the best way to do this is to do this with a substitution. Let's let u is equal to 4x squared plus 5y. du, we're thinking of y, as x as a constant here. Du is 5 dy. And so we would have integral x from 0 to 2 of integral u runs from 4x squared plus 5 times 0. So that's just 4x squared to 4x squared plus 5 times y is x squared here. So 4x squared plus 5x squared there. And then this is just u raised to the 1/2 power du dx. So what happened here? So the outside integral from 0 to 2 stayed put, that dx stayed put, dy got replaced with du. I also need to account for the du is 5 dy by dividing by 5 here. And the 4x squared plus 5y, that's u, so we have the square root of u, and then we replace the bounds here to get that, because it's a definite integral, so we need to replace our bounds. And so what do we have? Time for more room here. Integral from x from 0 to 2 of the antiderivative u to the 1/2 becomes u to the 3/2 times 2/3. There was a 1/5 floating around. Plug in u was 4x squared to 9x squared. 4x squared plus 5x squared is 9x squared. All of this dx. Okay, so what do we have here? We have 2 over 15. We can move that outside of our integral. Then 9x squared to the 3/2 minus 4x squared to the 3/2. 9x squared to the 3/2. The square root of 9x squared would be 3x. We don't have to worry about plus or minus because everything in sight here is positive. And then 3x cubed would be 27x cubed. The square root of 4x squared would be 2x. 2x quantity cubed would be 8x cubed dx. We can combine, and I'm just going to skip the steps here. You end up with 38 times 4, all of that over 15 if you crunch everything out. Very straightforward calculus 1 integral. Okay, so that is two examples about interchanging the order here. Very important thing to be able to do. And let's finish this off with a pre-class problem. So scheduled domain integration, express an iterated integral in the opposite order. No, I haven't even told you what the integrand is. You just leave f of xy as the integrand.